right, welcome everyone to this afternoon's webinar. This is the third of a series of webinars on connected vehicle applications and deployments. Today's speaker is Dr. Khan Azbeh, who is a professor at New York University in Department of Civil and Urban Engineering and director of the C2 Smart USDOT Tier 1 Transportation Center based at NYU. Khan also served as PI of the NYU team participating on New York City connected vehicle pilot, USDOT connected vehicle pilot led by New York City DOT. And today, Khan's going to give us a talk on simulation-based safety evaluation framework for connected vehicle applications for safety and operational measures. As a reminder, this webinar is being recorded and will be made available on C2 Smart's YouTube channel following today's presentation. So with that, take it away, Khan.
All right, so let me just share my screen and then maximize. All right, so welcome everybody. I hope you can see my screen. And also sometimes this kind of acts out and doesn't move the slide. So let me know if there's such a problem. So basically today, so we thought about doing these webinars for the portion of the work we've done for the New York City CV pilot. This was a much bigger project with a lot of players with that, which I will talk. But in this talk, I will focus on the type of simulation study that we did for safety evaluation. I'll try to get into some details. But at the end, I'll show you the report where you have all technical details if you're interested in a paper also that we recently published. So the USDOT CV pilot is, as I said, quite large project. We were lucky to be part of it with as a university partner with also our colleagues from CUNY. They did some tasks and we were involved in some other tasks, and our main involvement was on the evaluation of the safety aspects of the project. This the CV pilot in New York City mainly focused on safety and then has been tested to see how we can help New York City reach its Vision Zero goals when a system like this one is deployed at a larger scale. So that's why it's called pilot. So in this pilot, as you see here, there were 3,000 plus vehicles involved, 470 roadside units, and then a number of mobility and safety applications. And it was actually done in different locations in the city, FDR Drive, Midtown Manhattan, and Brooklyn side. So this was a monumental task done by New York City DOT mainly. And then we, again, as I said, we were part of this very exciting project, and we're very happy to do so. So here you see the number of stakeholders. Here I'm not going to name all of them. The main sponsors of the project is USDOT and New York City DOT, and New York City DOT is the lead in this project. And Mohammed Talas, where you see his picture on the right bottom, was really responsible for the whole project. And he was, I don't know how he did it, but it was an incredible effort on his side, as his team, the whole DOT. So, so you have to give all credit for them to get this done in a very successful way. As I said, the project was focused on safety applications with vehicle to vehicle, vehicle to infrastructure, and vehicle and infrastructure to pedestrian type of communications. And the main idea is basically to give drivers alerts so that they can take an action to avoid a crash or reduce the severity of injuries or damage to vehicles and infrastructure. Here you see the number of the names of the apps for each category, V2V, V2I, and mobility category. I'm not going to go through all of them separately, but some of them are kind of we're familiar with them, like emergency electronic brake lights, forward crash warning, intersection movement analysis. But there are also things like red light violation warning, speed compliance, and so on. So all these apps were programmed and incorporated into the test vehicles, and data was collected about each of them. There is on the left side, there is a link to the CV pilots program and specifically to the New York City Connected Vehicle Pilot Program. If you want to know more about all aspects of this, beyond this kind of focused presentation, which we will deal with how to simulate this kind of scenarios. So the team in the New York DOT's New York NYU side was me and Dr. Jenny Gao, and now Dr. Di Yang, who was a PhD student, and two other PhD students, Di Sha and Panzo. So we again like to thank all the players, especially City DOT, Cambridge Systematics, and JHK. And the team really did an excellent job in every aspect of the safety evaluation. So just a brief background for those of you who are not familiar with the CV pilot. There were 3 sites, Wyoming, New York City, and Tampa. And each site were basically focusing on different aspects. As I said, New York's focus was on safety. And you saw there were a bunch of safety apps in that sense. New York, in its as a whole, I mean, it's a very challenging environment. In addition to safety, there were many other challenges that we observed. For example, tall buildings, very heavy traffic, a lot of pedestrian traffic. So it makes this environment very challenging, but also one of the best environments to test connected vehicle technologies, because it kind of gives us an opportunity to understand many of the problems that we might face. I just want to, if it works in New York, it will work anywhere else. So I just want to say that, it really is important. So the US CV pilot deployment program has different goals. Obviously, one is like an early deployment, then measuring the benefits of this deployment, and then that's what we were mainly involved in that, and then resolve some of the deployment issues. As I said, for New York, and I'm not very familiar with other sites, but in New York there were some technical issues, for example, or institutional issues, and the team as a whole dealt with those. One of the issues that I want to mention very quickly, and then because it has some implications on the data that we use, it's the privacy issues. So NYU actually was responsible for IRB certifications and how the data saved securely, but DOT and its partners, they also did a lot of work on looking at different methods to make sure that the privacy is there, and then we don't know that individual vehicles movements and so on. So there were a lot of work on that, and that's why the data is not identifiable. It's just basically obfuscated, and then there's some limitations of that, but it had to be done to ensure privacy. And that was one of the institutional and technical issues combined that the team had to do. And then some of our evaluation procedures, we had to adopt techniques to accommodate those, because we're not really following individual vehicles. We don't know the identities and so on. So it's like more general. So we need to use techniques accordingly. So as I said, the primary goal of the pilot is improving safety, but there's also a secondary goal of improving mobility. Mobility evaluations were not done by us. It was basically Cambridge Systematics, and here OP led that effort. And then the idea is basically once you deploy, to see how the system performance metrics are acting, basically. What are we seeing? So we need to collect data to understand these system performance measures, and as I said, also address the privacy concerns and data collection costs and so on. These are again, I don't want to belabor too much on this. These are all the apps that were deployed. As I said, they were deployed in 2,000 vehicles. As far as I know, this is one of the largest deployments. And if you can guess, I mean, I've seen deployments with maybe 20 vehicles, 50 vehicles, 100 vehicles. But when you go above certain number of vehicles, then there are a lot of issues in making sure that the apps are deployed on time and they continue to work. And you see all kinds of these apps, so they should all work in harmony. So this was again a gigantic task. Okay, okay. So the safety analysis, which is the main topic of today, is looking at before and after the deployment of these apps, basically to understand if when you have an app that gives you, for example, for forward collision warning, does it really improve the safety? And to do that, we had to define a control group and a treatment group. So basically, control group is the group that we are using to understand if the treatment has a statistically significant impact. So there were a lot of back and forth and work with our team partners, especially with Kier OP, to kind of how to design this before and after test and how to design the control and treatment, which actually last 2 weeks ago it was discussed at some length. And then we decided to use both field and simulation data. So here, let me just say why we are also considering simulation data. Although we have a large set of vehicles, still it's not at this point scalable to a number of vehicles. It will affect the traffic in terms of what we are measuring. So you still need to do some simulation to understand if these apps are deployed on many more vehicles than 3,000. 3,000 is large, but given the context, the number of vehicles that travel in New York City is not that large. So you're not going to be able to do experiments the way you will do in simulation. And that's what one of the reasons we use simulation. And then when we use simulation, we use, if you look at the last box, and today this is what we're going to talk about, we use surrogate safety measures. So basically, we're not simulating crashes, but we are simulating surrogate safety measures. It means conflicts that will potentially lead to crashes. But in order to do that in simulation, you need to calibrate your simulation for both safety and operational measures. So traditionally, simulation is calibrated for operational measures to make sure that it replicates what happens in terms of operations, basically, without considering the safety. But in this project, we wanted also to calibrate the simulation to generate results that are consistent with the safety measures that we chose, which is the time to collision, and then make sure that simulation is calibrated from both perspectives. We also incorporated driver behavior models that are calibrated using the data that we get from the apps, from the deployments, and then we use a multi-objective stochastic optimization approach to achieve this calibration task. But we are not ignoring the data that we are getting from the AST data. So and then we are not ignoring the crash records and so on. So we in the report you will see a large discussion of how we looked at the before and after AST data, which is the data that you get from the devices in vehicles, for both control and treatment groups. Treatment groups are the people who are hearing the warnings and then responding to those. So we did that, but we basically focused also on the simulation to understand how the changing behavior of drivers will affect the safety. So simulation allows us to isolate the benefits from individual CV apps because we are in control of the app and what the driver is doing in the simulation, and then we can actually eliminate the impacts of some confounding factors that are impossible or not easy to do in real world type of experiments. We are using time to collision, a commonly used surrogate safety measure that we are obtaining from the vehicle trajectories as indicators of safety performance for both simulation and observed data. So basically, TTC is a very simple measure that tells you that if you don't respond to a slowing vehicle or to certain vehicle that you're following, and then accelerate, what is the time to collision with that vehicle? So it doesn't have to be an actual collision, but it's the risk of collision, basically. So that actually takes away some of the criticism about current simulation models, open source or commercial, not being able to simulate crashes, because we're not trying to simulate crashes. We're trying to understand the interaction between following and leading vehicles, and then see if that can be translated into some safety measures. So our simulation focused on the Flatbush Avenue test site in Brooklyn, New York. We took like 1.6 mile of the segment. It's a very heavily used urban corridor with 8 lanes for instruction. There are side streets that are feeding into the Flatbush Avenue. We incorporated those, and then we focused on morning peak between 6 and 10 a.m. We incorporated obviously signal information, bus information. So this is a very mixed traffic type of environment. You have cars, buses, trucks, pedestrians. So we were able to get all that into our simulation model. We use Sumo, especially in this case. It's important to use an open source model that allows us to make changes and easy to integrate some of the add-ons. So we use Sumo for that, and then we employed the API interface of Sumo, and then we were able also to run the model in a parallel mode because we had to run many scenarios. So so for the unique challenge is that in this case, we're not only calibrating for operational measures using travel time or traffic counts, but also with for safety measures. How to do that, you know? So we proposed a new calibration framework which combines traffic conflict techniques with multi-objective optimization, so that we can do this joint calibration or joint optimization, basically. So we have traffic conflict distribution of different severity levels categorized by time to collision, which I mentioned. And then we are also able to get real-world traffic conflicts from vehicle trajectories, from videos, recordings, and so on. So we have some real-world data, and then we are using that real-world data and the TTCs that are derived from the real-world data to calibrate our simulated model. So basically, the model is not only replicating travel times and volumes correctly, but it's also replicating the interaction between vehicles in terms of vehicle trajectories. So this is actually a kind of damning task, a lot of work. But once you do that, you're capturing this vehicle-to-vehicle interaction, which is a surrogate measure for traffic safety. We calibrated Sumo for 17 parameters. And then we also used an approach called a simultaneous perturbation stochastic approximation to achieve that calibration of multi factors that are also highly stochastic in terms of the simulation environment. So this is basically the overall simulation methodology. So we have a very involved way of data collection and processing. We use traditional data sources. Obviously, you need to know the network layout. As I said, you also need to know traffic conflicts. Then once you use that data to basically model development, and then you need to basically find out for which day or which days you want to calibrate your simulation. So in the past, when the data was not that abundant, we would take 1 or 2 days of data and we calibrate for that limited data. But in this case, we have actually a year-long, multi-year data for especially traffic speeds and travel times. So we had to do something a little bit more than what we do because we're not really working with very limited data. The performance measures are, as I said, operational measures, safety measures, I'll talk in a minute. And then we have a bunch of accessibility criteria. Some of them are well accepted, well-known criteria for federal highways. Some of them we had to develop for safety applications. And then we do the model calibration and validation, which is an iterative process. So let me just talk about this, the representative data identification. So basically we have defined days that are similar. And in order to do that, we need to use some well-known clustering techniques to find out which days are close to that representative day. So this was done by basically finding an average value, let's say for travel time or speed, and then find the closest days to the mean of samples. So and then we basically do Kolmogorov-Smirnov test to make sure that these days are similar in terms of statistical significance. And then we identify 96 days out of 320 days that we tested this for. And then we use that data to calibrate our simulation. So for the operational performance, we use an error function called root mean square percentage error. Basically, we are simulating and then comparing the simulation to observed values and then see how the error moves. And then we are looking at different acceptability criteria suggested by Federal Highway. Remember, this is a research project in some ways, but also it's a real world project. So there's a balance we have to achieve between research and real world. So since it's a real world project, we also have to satisfy some of the well accepted criteria so that the results are acceptable to the traffic engineering community. There's research in terms of calibration and adding a new framework that includes safety that is not in state of practice. So in that way, we're improving the state of practice and state of art. So these four criteria are proposed by the Federal Highway. So basically looking at outliers, looking at inliers to avoid overfitting, looking at bounded absolute error, like total of all errors between observed and simulated variables, and then looking at a systematic error, almost like an average error, like what happens, again, how this dynamic works between simulated and observed days. For the safety, we basically are looking at TTCs, time to collision percentages or probabilities from both the real world data and from the simulated data. And then we plot them, and then we use this goodness of fit measure, Kullback-Leibler divergence measure that is basically shown here. It's actually quite simple. It looks at the proportion between the probability of certain event divided that is observed versus simulated. So basically, you're trying to match this measure with the simulated and observed data. So basically, if in the percentage of simulated X event is equal to the percentage of observed X event, then there's no problem. So this good. So it will be 0. And if you have all these individual ratios equal to 0, let's say, or something very close to 0, then this DKL will be quite small, and the smaller the better. So basically, you want the observed to be very close to the simulated. And then we define an objective function, which is in the bottom, and we're trying to minimize that objective function, which is the root mean square, and so for the operational, and then this DKL measure for the safety with some weights. And then we don't have time to talk about it, but then we use the weights to make sure that we normalize for the actual values of root mean squares and the DKLs, because they're not in the same range. So this has been taken care of. Okay, so the video, so we basically use the video from traffic DOT traffic cameras when the traffic cameras are available. Sometimes there's a problem with that because those cameras may be obstructed, or the height of the camera might not be enough to capture all the movements. Sometimes the camera might be tilted, so you might not get the trajectories. So other types of, we tried also other type of video recordings when you can get a bird eye view of traffic, but that's limited. So for example, you can we tried to put a camera in our previous work and this one on top of a very high-rise building, and then try to record it from there. So if you have bird eye view, obviously you can get much better trajectories. So the calibration process, as I said, it's kind of complicated, and it's an iterative process. So basically, every step we're trying to run the simulation and then see if there's a change in the error function. And then this is done using a gradient estimation method. If the gradient continues to go down, we continue to make changes to our variables, basically perturb them, and then run the simulation again. So here, one of the problems that each simulation run takes long time to run, and then each simulation run cannot be used individually because of the stochasticities. Even for the same values, you might get different results. So you need to take all that into account when you do your calibration, and then you need to do this in a quite involved way. So basically, how do we find the sample size? How many times we have to run the simulation? So basically, we use a method that is well known, basically a variance reduction method. So here, just basic steps of that. We start with an initial number of repetitions of simulation for a given starting point for all our variables that we want to calibrate. And then we calculate our mean value for and then variation for different runs. And then we determine an error, and then we calculate a relative error, and then we decide the level of significance. So meaning at what level of significance we want to be able to say that our simulation results represent the reality, the real population, basically. And then we use a simple t-test to test that hypothesis. And if we satisfy the hypothesis, then we say this point estimate x bar of the mean value of the variable we're trying to calibrate is good enough. We stop. If not, we go back and increase the sample size. So that is actually takes might take many runs, or you can, in general, the practice is like you fix your runs. You say 5 runs, the mean value is fine, and I'm just going to use that one. But that's not true for different types of simulation networks, because the variability might be high. So you might have a mean value that's too spread, and all the values will be too spread around that mean value, so that it might not be acceptable. So you might need to have more runs. So fixing the number of runs, 5, 10 might not be a good idea. So you need to use more kind of reliable methodology to decide how many runs you have to do every time you evaluate your mean values from the simulation. And all that comes from the stochasticity that exists in the initialized parameter values, and then the stochastic nature of the microsimulation. And the microsimulation has its own inherent stochasticity, like real world, and the variance of the input data also has some stochasticity. So you need to really take into account all these stochasticities. And then as you see here on the right side, we see how variables converge as a result of the calibration process. So you start with an initial value, let's say for the maximum speed or acceleration, and the more you do your calibration, it will converge to a number that is basically your mean value for that variable, let's say deceleration, maximum speed, or vehicle reaction time, and so on. And then that one thing that we have to understand, that's a mean value, and then there'll be some stochasticity around it or some noise when we put that back into simulation, and we need to take that also into account. So this is basically the part that everybody knows, the operational measures. So we look at the link volumes and travel times, and then we calculate them so we have these values for the average day, and then we're looking at them, like you're looking at the representative day values in blue, and then these are simulation runs in yellow triangles, and then we look at them where they are. Are they too far from the average day? Are they within some envelope? And if it is, then you say, okay, I'm doing well. So basically you run the simulation several times, and then you look at your output, and you want to make sure that every time you run your simulation, with all these stochasticities, it doesn't go too far away from your representative day. So it's always around that blue line, and then we define this basically envelope to see if any points fall outside the variation that you observe from your data. Okay, as I said, there are other measures that Federal Highway suggested, like bounded dynamic absolute error and bounded dynamic systematic error. So we calculate that also for the simulated observed data. And then in the bottom of this table, you see the equations that we use to calculate those, and then they should be smaller than some threshold that's accepted. And then in our case, they were all smaller than threshold. That means they were all acceptable. And as a kind of a side note, this is done to ensure that the average simulated results are close to the observed original representative day and are not excessively over and under estimates. So basically, you always want to be close to the average. And this measures ensure that. So now it comes to safety. For safety, as I said, what you do is you basically plot the observed TTC values and the simulated TTC values. So basically, these plots show the percentage of the time to collision values that you observe from the field data and from the observed data. And I talked about it a few minutes ago about the DKL divergence measure. We calculate that measure into two, and then when we did that, we found out that actually for our simulation, the conflict distributions after calibration, this DKL measure is very small. So this is what we want. We want to be as close to zero as possible. If this was large, it means px, qx is too different, then you get a larger value, and that's not good. But actually, even if you look at the distribution graphs, you see that distributions are very similar. So this is kind of visually also, you can understand that the observed and simulated results are close to each other. Now, after we did this baseline calibration, now we want to go forward and integrate the CV applications in our simulation. So basically, program the CV applications as close as possible to the real world, so that we can simulate now the vehicles with CV applications using the calibrated simulation and how they will affect overall safety and traffic measures. So we we spent a lot of time on that. We basically chose CV apps for their significance, their importance, and also we tried to avoid the most complex CV apps. There was one that will be very difficult to program. We also wanted to focus on CV apps that we know that there'll be enough data for simulation, calibration, and verification. So in the end, we chose like 7 CV apps, 5 V2V, 2 V2I, and the list is here. So forward collision warning, electronic emergency brake light, blind spot warning, lane change warning, and so on. So these are the ones that we programmed into the Sumo simulation so that we can now run scenarios and then see how they affect safety and operations in a larger deployment scenarios, for example, not just 3,000 vehicles, but can be more different percentages. And actually here on the right side, you see kind of a visualization of electronic emergency brake light. So let me see if I can run. So vehicles approach the intersection, and then the vehicles that are the red ones are braking, the purple ones are responding to that, and then we collect data from this kind of simulations. So this is the data after in the after period, June to September, to understand also the driver response, real driver response in the presence of these apps. So now we had the calibrated baseline model. We have programmed our 7 CV apps, but we also want to see how drivers reacted in real world in the presence of these different apps. So we have this data, and we will use this data now to recalibrate our after model to kind of reflect the actual behavior of the drivers to these apps. So because in the before period, there's no apps, and we're just calibrating for normal driving conditions. Now we are calibrating the driver behavior for the instrumented vehicles that we are going to simulate for using this this data. And then in this part, we focused on the car following model that we are using in Sumo, this intelligent driver model. And the ones that you see in the red box are the parameters that we calibrated for CV drivers. So from the field data, we are getting the variables that you see in purple box: spacing, speed, approaching speed to the difference, differential in approaching speed to the leading vehicle. We use those to calibrate these variables in the red box. And then to do that, we used different algorithms. We still used SPSA, but we also used some genetic algorithms to calibrate these variables and then see if they would give us different results. And then this is some of the calibration results for an example for sample vehicles. And then you see after calibration, actually the sample vehicles trajectories are very close to observed vehicle trajectories. And then NSGA2 algorithm, the genetic algorithm, gave the best solutions, the closest match in terms of vehicle trajectories generated from the simulation, calibrated simulation, plus the observed numbers. And then we took all of that and then tried to understand if these warnings generated by the apps made a difference. So this one shows you the simulation-based analysis results. And then the first three bullets are from the data. So there were 2,000 plus events that we observed in red light violation warning. And then we saw that compared between before and after periods, there were 150 fewer red light violations. So that means overall the apps helped reduce the number of red light violations compared with the before period where there was no such a warning. The driver response also significant in terms of decelerating to avoid running the red light. And then when we looked at the same thing on the simulation using the surrogate safety measure, we showed that there's an improvement in the TTC, and it was statistically significant. That also kind of told us that the improvement we saw in real world data was also being able to, we were able to recreate that in the simulation. So, so from both simulated and observed results, we show that this app actually improved safety. These are mainly based on the simulation-based analysis. And then you saw for forward collision warning and emergency electronic brake light, although there were some changes, but they were not statistically significant or marginally insignificant. For blind spot warning and lane change warning, we found out that the simulation results gave us significant improvements in terms of safety, which is TTC, time to collision. And these were all consistent with the observed results. So simulation was able to generate results that are consistent with the field data. We also did analysis of pedwalk, pedestrian crosswalk. From the real world data, there were 20 events, so not too many, but we were able to simulate that again using surrogate safety measure, and we show that there's an app like that running in these connected vehicles. They will be able to improve safety, i.e. TTC values, in a statistically significant manner. So the conclusions are, as follows. So basically, in order to do this kind of studies where you have both operational and safety concerns, you need to have a different framework for calibrating the simulation. You cannot just use a simulation calibrated for operation purposes. And then that's what has been done here. We proposed a new calibration framework that combined that. And then we use the SPSA algorithm to take into account the stochasticities, both in the model input data, to achieve this multi-objective stochastic optimization. The results of the calibrated parameters improve the performance of the simulation model to represent real-world conflicts as well as operational conditions. So we were able to show that the model works well for both objectives. Then we basically extracted AST data for before and after periods for the pilot test. And then we found out that there's a behavioral change for people in the treatment. That means people who are hearing these warnings in the treatment group. And we incorporated that into our simulation when we're using the simulation for simulating safety applications. So this is the second level of calibration that we did. I think this is also quite unique. And we were able to do that because we had enough data to calibrate the car following model. And then we showed that the simulation-based approach was able to generate similar results in terms of safety benefits, but we could run the simulation for larger number of vehicles, and we can actually isolate the benefits of individual CV apps and eliminate the impacts of some confounding factors, which is very difficult to do in a field test unless you're going to have many more numbers of vehicles and much longer evaluation time. So we could do all of that. That's very difficult to do in real world in the simulation. So we think that we can improve the simulation approach, can be improved to basically help to do crash-based safety analysis, and then maybe you can use different surrogate safety measures. But I mean, one of the outcomes, research outcomes of the study, if you do the right types of calibration, and then if you have relatively good data, simulation can be a valuable tool and scalable tool to test different ideas for this kind of apps. So these are two publications. One is the system performance report, so you can download it. It's available online. The other one, it's a paper that basically focuses on the calibration work that I just discussed here, and has many more technical details. And again, you can download it from the link. There'll be another webinar next week. Basically, it will be a roundtable with some very active and top participants in this project. And then we will discuss lessons learned, future research and deployment. And please register and attend that meeting, that roundtable, which I think will be very, very interesting. So with that, I'm going to stop. I don't know, I think 10 minutes to 2, and I'll take questions if you have any questions.
Yep, so if anyone has any questions, please use the Q&A button at the bottom of your screen, or raise your hand using the raise hand feature, and we can call on you if you want to speak your question out loud. But feel free to type it in the Q&A if you want to type it out. So far, not yet. So we're here to take your questions if you have any.
And of course, you can email me questions. You can watch the video presentation and come back to us.
Okay, so we have a question here from Jean McHale. Go ahead, Jean. You are muted if you unmute yourself.
Okay, can you hear me now?
Yep.
Great presentation, Khan. Thank you. One question I had when you had to write the code for the CV applications in the simulator, well, in the simulation, did you get any information on the algorithms and all the assumptions for the actual applications running in the vehicles, or did you kind of create it from scratch?
We had some basic information, but some of it was assumptions that we made. But it's a mix, you know, so it wasn't like we didn't really imagine how they would work. Basically, we used the app specifications that were available to us to create apps in the simulation that are as close as possible to the real world. But, you know, there are some assumptions, obviously, and they might be slightly different than what was deployed in real world. But we had information about each app.
Okay, great, thank you. And well, I guess one follow-up, is the code that you produce for those apps, is that something that you're sharing, or is that?
I think it's all shared, but
okay.
Yeah, I think if it's not, we can share it with you.
Okay, great, thank you.
All right, any other questions? Again, you can use either the Q&A or raise your hand and I'll call on you. Okay, so just to give it another minute, I will just once again plug our event next week, which is Wednesday at 4 p.m. Also on Zoom. You can register on the C2 Smart website, or however you receive this invitation, you should have it there as well. It's a roundtable featuring different participants in connected vehicle programs. We have Dr. Asbe, joined by Carl Wunderlich from Noblest, Billy Chupp from Volpe, Mohammed Talas from New York City DOT, and Cecilio Concas from University of South Florida. We're going to have a roundtable to discuss connected vehicle applications and deployments and kind of the future directions for the research and also deployments throughout the country. So, Khan, I don't know if you want to tease anything about where you think the future of this field is heading and what's next beyond even safety evaluation for CV deployment.
Yeah, I think it will be a great roundtable where all these individuals are very experienced in CV pilot deployments and previous work. And I think now is a good time to look into the future. And I think there'll be a very exciting discussion. And actually, one of the things that I would ask to this audience and whoever they're talking to, please invite your colleagues and friends, because we want to make it as interactive as possible. We'll be discussed. I mean, we'll be open for questions. No presentations. We will not make any presentations. We will basically have an open discussion, and the questions are more than welcome. I think it should be driven not only by what we say, but also what we hear from the audience and their questions. So definitely, please attend and contribute to that.
All right, so with that, we'll wrap up today's session. Thank you everyone for joining. This webinar was brought to you by C2 Smart, a USDOT University Transportation Center, and on behalf of the extended USDOT Connected Vehicle Pilot Team. Thank you, Khan. Any closing remarks?
Thank you, everyone. Thank you.